please go ahead. He will talk about the average Gromov hyperbolicity and the Parisi ansatz. Please.
Okay. Thanks, Daniel. So I would like to thank the organizers for the invitation to this very nice meeting, and very nice city and food, and this is really wonderful. So today I'm going to talk about this recent work with Leila Sloman, who is a student at Stanford. So let me begin with this one slide. So spin glass. Many of you may have heard about spin glasses. We study them in probability and mathematical physics. It's a kind of magnetic object with properties that are different from ferromagnets. So let me just leave it at that. Also, I'll not go into the details of spin glass model. So let's just say a mathematical model for spin glass. What it does, is a little different than the usual probability models that we see in probability theory. That in probability theory, we usually see a probability measure on some space. In spin glass theory, usually this probability measure itself is random. So you have a random probability measure on some space, and we want to study that. And typically, the space is either the hypercube or the sphere. So it denotes the spins of n particles. So you have n particles, and they have their spins, which are either +1 or -1, or they can take real values also. So in this talk, this will be either of these two. So we are concerned with random probability measures on the space. And one of the most famous examples, you may have heard the name, is the Schoenstern-Kirkpatrick model, which has been widely studied. And here, this mu n is called the Gibbs measure, and this is called this configuration space. So these are terminologies that we will which are ±1, let's say. Let's just think of it that way. And an important quantity in spin glass theory is what's called the overlap, which is just this average of sigma I1, sigma I2. And if these are all between all +1 or -1, then this overlap is from -1 to 1. So it's a number between -1 and 1. And what the study in the theory of spin glasses is that if you have two configurations drawn independently from the Gibbs measure, what is the behavior of this overlap? And that's important for various reasons. So we study the properties of this object for various important reasons. Okay, so this is what I just said, that the overlap is between -1 and 1. Okay. And suppose we have an IID sequence of configurations drawn from the Gibbs measure mu n. These are called replicas. So this is another terminology that they use in spin glasses, that you have this sequence of configurations. Note that the superscripts denote configurations. Sigma 1 is an n tuple of ±1s, and sigma 2 is another n tuple of ±1 spins, and so on. So we have various n tuples of these things, and these are called replicas. And you may have heard of this terminology called the replica symmetry breaking and so on. So the replica refers to these. And the overlap between two replicas, sigma I and sigma G, is usually denoted by Rij. So R12 is the replica is the overlap between sigma 1 and sigma 2, and R13 is the overlap between sigma 1 and sigma 3, and so on. So this is all just terminology. And so just to recall, now we have this configuration space, which is, let's say, -1, 1 to the n, the hypercube. And then we have a random probability measure or a random Gibbs measure on this hypercube. And we have this configuration sigma 1, sigma 2, etc., drawn from this random Gibbs measure. And we want to understand these overlaps. So I haven't defined the measure yet, so just think of it as some abstract measure that you have. And we want to study these overlaps, R1 to R13. So for example, if the Gibbs measure was just uniform measure, which is not random, then these overlaps would be close to 0. Because if you have two configurations drawn from the Gibbs measure, which is drawn from the uniform measure in the hypercube, then their overlap is with high probability close to 0. And so that's not a very interesting situation where you have all these overlaps close to 0. In spin glasses, interesting models of spin glasses, the overlaps can, may not be concentrated. So they may actually fluctuate. So there may not be concentration. Okay. So here's the Parisi ansatz. So Parisi conjectured that in various spin glass models, you have the property that in the n tending to infinity limit, this overlap has a property that R12 is with high probability. So this, I'll show you a precise meaning of this. But in the limit, R12 is bigger than the minimum of R13 and R23. So it's like the following. So you have this spin configuration drawn from the Gibbs measure. So you have you have an n tuple of -1, 1, spins drawn from a certain measure, and you draw 3 of these configurations from this measure. The first configuration, second, and third. And you compute the overlaps between all pairs, 1 and 2, 2 and 3, and 1 and 3. And with high probability, you will see that R12 is bigger than or equal to the minimum of R13 and R23. And this is, something that Parisi observed in simulations, and that's what I heard. And he conjectured that this is true, and based on this, there was this big theory that was built, okay, based on this ansatz. Okay. So this is known as the Parisi ultrametricity ansatz. Yes. That's what I'm trying to get at. Okay, so that's the main thing. So what is this picture? So there has been a lot of progress about what is the picture. What is going on, and it took from 1980 to now 40 years it took to get more or less a grasp of this picture mathematically. Okay. So this is the basis of the Mézard-Parisi broken replica symmetry method for solving spin glass models. But this method is still a mystery. It has not been made rigorous, but there have been alternative arguments, rigorous arguments that have been found. So I'll talk about that. So there's following this long line of contributions by many authors. This conjecture was finally proved by Dmitry Panchenko for certain classes of spin glass models that satisfy these equations known as the generalized Ghirlanda-Guerra identities. Okay. And what this says precisely, so what I stated as Parisi's conjecture was very vague, so this is a much more precise statement. So what this says, Panchenko's theorem says that for these models, the models that satisfy these generalized Ghirlanda-Guerra identities, you have this property that you look at this event, take any epsilon, look at this event that R12 is bigger than the minimum of R13 and R23 minus epsilon. So you allow a little bit of error. And look at the probability of this event under the Gibbs measure. So this angle bracket thing here is the probability of this event under the Gibbs measure. So there are 2 levels. So the Gibbs measure itself is random. So once you have the Gibbs measure, you're picking 3 configurations. Okay. Then you're looking at this event that R12 is bigger than the minimum of R13 and R23 minus epsilon. Okay. And you're looking at the probability of that. And then that probability itself is random. So you take the expected value of that probability. So that gives you a number. And what the theorem says is that this expected value of this random probability is tending to 1, which means that the probability itself must be tending to 1 with in probability. Okay. So it's a slightly complicated statement, but you can see what's going on. So essentially it's saying that with high probability, this inequality is going to be satisfied approximately in the n tending to infinity limit. So, okay. So this is the theorem, and these identities have been proved in large class of models. They have not been proved in some, but generally, there is a large class of models in which we now know that these identities hold, and therefore this ultrametricity holds. So that is the proof of the ultrametricity theorem. Now, so the picture, what is exactly going on? So you have this probability measure on this hypercube, and you have these 3 configurations drawn at random, drawn from this probability measure, and it has this property, R12 is bigger than minimum of R13 and R23. And if the overlap itself is concentrated, it's like a constant, then you can understand, of course, this is trivially true. But if it's not a constant, if it's fluctuating, if the probability measure is such that the overlap itself has fluctuations in the n tending to infinity limit, then what is going on here? What is the picture that causes this? So what the physicist will tell us is that this happens because this infinite volume limit can be decomposed into hierarchically organized pure states. Okay, so I'll tell you what this means. So this is what they conjectured. And what this means, I'll show you a picture in the next slide, but what this means is the following, that this configuration space of all possible spin configurations admits a hierarchical clustering, which just means hierarchical clustering just means that you have a big cluster and then the big cluster is divided into smaller clusters and the smaller clusters are divided into further smaller clusters and so on. So there is a hierarchical clustering of the configuration space. And there is a number attached to each cluster so that if two configurations are drawn independently from the Gibbs measure, and you know the smallest cluster which contains both configurations, then with high probability you can roughly tell what the overlap between these configurations are. So it's determined by their location in this tree. So it's like the configurations are organized as the leaves of a tree, and then the node at which they meet. So if you take any two configurations and you look at the path from the configurations to the leaf, they will meet at some point, and where the meet will determine what the overlap is. So this is this kind of organization. So let me show you a picture, and this will become more clear. So here is the whole space, and then alpha is a big cluster, and then beta is a smaller cluster, and gamma prime are further smaller clusters. And let's say the configurations that you have drawn from the Gibbs measure the first one falls in this gamma, the second one in this gamma prime. Then the picture will tell you that the overlap between these two configurations with high probability is approximately q beta, the number attached to this bigger configuration beta, because this is the smallest cluster containing both of these configurations. Okay, so it depends on the smallest cluster containing both of these configurations, and this is roughly, so again, this is not a precise picture because this is just a conjecture. So the goal of this talk is to give a precise sense to what this means. So there is this, this space is divided up in as the leaves, sort of like the leaves of a tree, and then with high probability, this kind of situation happens, that R12 is approximately this q beta. So again, so as you see, this is kind of complicated thing to make sense of. So if the overlap can only take finitely many values in the infinite volume limit, then it's not difficult to prove this. So it's an inductive argument. Using an inductive argument, you can prove this, and this is called the KRSB model. So replica, k steps of replica symmetry breaking, where the overlap can take only k possible values. And this is the basis of the heuristic sketched in the physics papers. However, often you don't have this. So usually, in the more common situation is that you have full replica symmetry breaking, where the overlap can take the limiting distribution of the overlap is continuous, okay? Where you don't have atoms, and there it's not clear how to make sense of this. Okay? So recently, in very recent years, in the last 3-4 years, there has been some progress on this construction of pure states, this deeper understanding of what is actually going on. So one is what's called the pure p-spin spherical models, where this pure state construction was given by Subag, and it builds on the contributions from many people. So one of them is an expert on spin glass in the audience. Gerard is here, so this in this pure p-spin spherical models, we now have a good understanding of what this pure state construction is. And the second class of models that satisfy the models that satisfy generalized Gillarda-Gouin identities. So for these models, this construction of pure states was given by Panchenko in the infinite volume limit, but the bigger challenge is to prove it in finite volume, what this exactly means, and this was recently given by Jagannath in the setting of large but finite n. Okay? So there has been considerable progress on this question, giving this construction of pure states. Now, however, one should expect that this pure state picture would hold whenever this ultrametricity ansatz is satisfied. So it shouldn't be a different proof somehow. So it shouldn't be you have this ultrametricity, and somehow as soon as you have the ultrametricity, you should be able to say that there is this hierarchical organization of pure state. And this is the main result, well, the first main result of this talk. So it's a consequence of a more general thing. that whenever you have this ultrametricity ansatz, any probability measure that satisfies the ultrametricity property, you can have an automatic construction of pure state. Okay. So let me first generalize this. So it is believed that this ultrametricity ansatz and this generalized Gill-Ludwig identities are equivalent, but this has not been proved. And there are also important models, this Schenker-Kirkpatrick model that I mentioned, where it is known that this generalized Gill-Ludwig identities do not hold, so you can prove that. Now, in the Schenker-Kirkpatrick model, the thing is that the overlap is not supposed to satisfy the ultrametric property. What is believed is that the absolute value of the overlap satisfies the ultrametric property. And to account for such cases, let us formulate a generalized version of the answer. So you'll just say that, just in case somebody is able to prove in the future that in the SK model, this absolute value of the overlap satisfies the ultrametricity ansatz. So to account for those cases, let's say this model satisfies the generalized Parisi ansatz if for some bounded measurable function and any epsilon you have this. So instead of the overlap, some function of the overlap satisfies this, like the absolute value. Okay? So with this function, so generalized Parisi ansatz with some given function f, and so let's yeah. Yeah. Okay, so here's the main theorem about spin glasses. Ultrametricity implies hierarchically organized pure states. So consider any sequence of spin glass models that satisfies the generalized Parisi ultrametricity answers for some bounded measurable function f. Then there are sequences epsilon n and delta n tending to 0 such that with probability 1 minus epsilon n, that is with high probability, the following happens. There is a hierarchical clustering of the configuration space. So as I said, this tree-like organization, so this big cluster and there are smaller clusters within the bigger clusters and so on. There is a hierarchical clustering such that the number of clusters is finite, but may depend on n, it may be growing with n. Each cluster is measurable, so this is to account for cases where sigma n is not a finite space like the sphere, so we have to say something about measurability. And for each cluster alpha, there is some number q alpha that is a function of its depth in the hierarchy. So it just depends on the depth of the cluster in the hierarchy. With the property that if you pick two configurations from the Gibbs measure, then f of R12 is close to this q alpha with high probability under the Gibbs measure. So this delta n is also tending to 0. So this is so this alpha here is the smallest cluster containing these two configurations, sigma 1 and sigma 2, drawn independently from this Gibbs measure. So this is a completely precise statement of what I said before, that this is what's going to happen. So you just have to start with the assumption that this Parisi ultrametricity ansatz is satisfied, and from that you automatically have this complete construction of these pure states. So there is, with high probability, there is a hierarchical clustering whose size may grow with n. But, it has to grow with n if you have a full replica symmetry breaking. So there is a hierarchical clustering, and each cluster has a number q alpha attached to it, which depends on the depth of the cluster in the hierarchy. And with the property that if you pick two configurations, then this f of the overlaps is given a function f, which may be the absolute value or maybe the identity function, just fx equals x or fx equals absolute value of x or whatever it is. Then this f of R12 will be close to q alpha with high probability, where alpha is the smallest cluster containing both configurations. Okay, yes, sure. So the clusters is for the full space. So the full space, so there's clustering on the full space. I'm not doing clustering on the subspace. No. Clustering is on the full space. So that's not part of the theorem, but in the special cases where there are now rigorous proofs of this clustering, like in Jagannath's paper, he can prove more with using the properties of the system. So this only says that as soon as you have ultrametricity, any system, not spin glasses, any system you have ultrametricity, you have this construction of pure states. Okay, so okay. So what, how do I prove this? So first some remarks. So note that this theorem works for finite replica symmetry breaking as well as full replica symmetry breaking. And it is a corollary of a more general result about almost hyperbolic metric spaces. So this is actually the main result, and this is what I'm going to present now. And this the spin glass picture comes as a corollary of this. Okay, so now, even if you are not familiar with spin glasses, you can forget about it because this is going to be something completely different, and then we'll connect it to spin glasses later on. So this is, even if you're lost now, you can catch up because it's completely a new topic. So let SD be a metric space. So any metric space, there's this notion of a Gromov product of 2 points xy with respect to a third point, defined as the Gromov product of xy with respect to a third point is half of the dxz plus dyz minus dxy. So you can clearly see this is non-negative by the triangle inequality. So this is called the Gromov product. And a space is called delta hyperbolic if for any x, y, z, and w, the Gromov product of xy with respect to w is at least the minimum of xz with respect to w and yz with respect to w minus some small delta. Okay? So if this happens, it's called delta hyperbolic. And you immediately see this has the ultrametricity flavor here. So, Gromov hyperbolic spaces were introduced by Gromov and have been very successful in many domains. The smallest delta for which this is satisfied is known as the Gromov hyperbolicity of this metric space. Okay, I'll tell you what this means, what is going on here. This condition is known as Gromov's 4-point condition. And if this is satisfied for all x, y, z for a given w0, so you can fix w, if for a fixed w, if this holds for all x, y, and z, then you can prove that it's satisfied for all w with 2 delta in place of delta. So it's basically, you can take a 3-point condition. You can fix your w, and it gives an equivalent notion. Okay? So we can equivalently define the hyperbolicity using a 3-point condition by fixing some w in the space. And if this is satisfied for all x, y, z with some fixed w, then we say that the space is delta hyperbolic with some base point w. So what does this mean? What do these spaces look like? If it's delta hyperbolic for some small delta, what does such a space look like? It measures how tree-like the space is. Okay. So to make this connection, we need to recall the notion of real tree, and this has real implications. So if this Gromov hyperbolicity is used in the study of phylogenetic trees, in applications. They want to see how tree-like certain spaces, and then as soon as you have some measure of distance, some notion of distance, you can compute the Gromov hyperbolicity. So what is the real tree? If T rho is a metric space, and x, y are 2 points, an arc from x to y is the image of a topological embedding of an interval, starting at x and ending at y. Okay. And a geodesic segment is an embedding which is if the embedding is isometric, it's called a geodesic segment. So a metric space is called a real tree if for any xy there is a unique arc from x to y, and this arc is a geodesic segment. Okay? So it's basically like a tree. So you just think of it like a tree where the edges have some lengths, and that's it. So, but this general definition allows infinite spaces and uncountable spaces and so on. So real tree with a distinguished point R is called a rooted real tree with root R. So now it's easy to show that a metric space is zero Gromov hyperbolic if and only if it's isometric to a subset of a real tree. Okay, so that's a theorem. And that's not a very difficult theorem, so you can prove this, that it's zero hyperbolic if and only if it's tree. Now, what about delta hyperbolic for some small delta? Is it approximately isometric to a subset of a real tree in some sense? So that's a question that you can naturally ask when you say that you're trying to measure how tree-like the space is. And indeed, this is true, but with a small catch, which is that S has to have finite cardinality. So you can prove this kind of approximate tree result only if S has finite cardinality, because the error is proportional to delta log of the cardinality of S, and this cannot be improved. Okay, because it can be shown that it cannot be improved, and the proof uses induction on the size of the space. So here is the theorem. So I don't know if they proved it, but I think that's the first place. I couldn't find it before that. So let SD be a delta hyperbolic metric space with base point W and finite cardinality, and let K be a positive integer so that this happens. So basically K is a log of the cardinality. Then there is a real tree so that, well, forget about this, so that there is an approximate, isometry between these, between S and this, its embedding in this tree, and there is this error, this annoying part, which is error. So this is not really an isometry, so there is this problem, and for this you cannot go to infinite spaces. So you cannot have a version of this for infinite spaces. Okay. Now, one problem with Gromov hyperbolicity, so this is, has been hugely successful. So Gromov studied it in the context of group theory, but later it has been extended to other things, and has found a lot of success. But if you go beyond groups, so groups are nice, okay? But if you go beyond groups, there is a problem that this is a worst case condition. So the space is not delta hyperbolic even if it fails for a single 4-tuple, okay? So it says that for all 4 tuples, it has to be satisfied, right? So if it fails even for a single 4-tuple, it's not a Gromov hyperbolic, delta hyperbolic. Well, well, that's easy to find out if you do Google. I mean, if you, it has so in in group theory it has initially Gromov's work, and then on the complete opposite side of the spectrum nowadays they use it in phylogenetic trees, that kind of thing, and then in between there has been a lot of, so this book of this is actually a book. So here they mention a lot of different things where they apply in pure mathematics. There has been a lot of applications in topology and other things. So you can imagine, there are many spaces which are approximately, tree-like or hyperbolic space, and it's a natural notion to measure hyperbolicity. And okay. Now for the construction of pure space in spin glasses, we did an average notion of hyperbolicity. So in spin glasses, we saw that, this hyperbolicity condition holds with high probability. So there is no way that we are going to get an absolute condition that is holds for all points in space, and we cannot get that. I mean, our space is the hypercube, so of course it's not hyperbolic, right? So we cannot get it for all points. So we need a notion of average hyperbolicity, where this 4-point condition holds in most but not all cases, where most is with respect to some Gibbs measure. So this has been considered in this literature on networks and phylogenetic trees, but mathematical properties are not understood. So this is the main result that I'm going to present, that I'll define a notion of average hyperbolicity, and then I'm going to present an analog of the embedding theorem that you have for Gromov hyperbolicity. There is an analogous embedding theorem, but that has no loss in terms of the cardinality. So that does not involve the cardinality of the space at all. As soon as you go to average hyperbolicity, you can get rid of that factor, and you can have an actual embedding theorem that holds for any space. So this is what I'm going to show. And the proof is based on Szemeredi's lemma from graph theory. So this is a different connection that you have. And there is a reason why, there is a reason why this log factor doesn't appear in this in this theorem, and we'll come to that. So. Okay, so first we have to define average hyperbolicity. So we'll go beyond metric spaces. We'll just have a set S equipped to the countably generated sigma algebra and a probability measure. So we'll have a probability measure, so we need a sigma algebra for that. And for technical reasons, we need countably generated. And then you have a similarity function, which measures how similar are 2 points x and y. So instead of a distance, we'll just have this similarity measure, Sxy, which is symmetric. And they generalize the idea of a Gromov product. So the Gromov product, remember, with a base point w, you have this xy w, and this is also symmetric. And if S is scaled to have diameter 1, so we'll consider finite diameter spaces, let's say. And with respect to separable metric, so then this Gromov product is a similarity measure. So instead of a Gromov product, which is a special kind of similarity measure, we'll consider much more generally. You have a similarity measure. And we will say that this 4-tuple, the S together with sigma algebra probability measure and the similarity function S, is delta hyperbolic in the average sense if this is less than delta. So what you do is the following. You choose x, y, and z, 3 random variables from this probability measure. You look at the minimum of sxz and syz minus s of xy, and you want this to be non-negative, this to be non-positive. So what you do is you take its positive part and take its expected value. And if this is small, we say that the space is hyperbolic. So the smallness of this will imply that with high probability, this thing is at least this minus some small constant. Okay, so you take the positive part of this, this difference. And so this is, now we have a general notion. So you have a space, we have a similarity function, a similarity between 2 points, and then we look at this minimum of Sxz and Syz minus Sxy, where Xy and Z are from this probability measure. We take its positive part, expected value, and that is a measure of hyperbolicity. So it's just a direct, transfer from Gromov's notion, worst case notion, to an average case notion. And where the averaging is now with respect to some given probability measure. Okay? So there are parts of the space which can be ignored if this probability measure is small on those parts. So this is our notion of delta hyperbolicity, average Gromov hyperbolicity. Okay, so now we want to show that any space, so any space which is delta hyperbolic in this sense for some small delta is close to being a tree. So we now have to say, what is this close to being a tree, what this means. So recall that a graph theoretic tree is just a connected undirected graph without self-loops or closed paths, so it's just a tree coming down like this. And a rooted tree is a tree where there's one distinguished node, and a leaf is basically the bottommost level. So if it's not the root and it has degree 1, okay, that's a leaf. So we'll say that a tree with root R is compatible with our space if the following three conditions are satisfied. So S is a set of leaves of the tree. So I'll show you a picture. So you have your space S. You want to express it as a set of leaves of a tree. Okay? This is actually equivalent to the notion of hierarchical clustering. So hierarchical clustering and expressing the space as the leaves of a tree are basically the same thing. Okay? So S is a set of leaves of T. T minus S is finite. So this, even if S is infinite, T minus S will be finite. So this is what we'll consider. And for any node V, which is in T minus S, the set of leaves that are the descendants of V is a measurable subset. So this is a technical condition. So this is just for proofs. So T gives a hierarchical clustering of S into a finite number of measurable clusters, and conversely, any hierarchical clustering of S into a finite number of measurable clusters defines a compatible tree. So it is a one-to-one correspondence between a compatible tree and a hierarchical clustering into measurable clusters, a finite number of.
So here you're excluding the full representation.
No, so I'm not excluding because, so as n tends to infinity, this tree will become larger and larger. Yeah, so I'm allowing that. So for example, for xy, let xy_r be the Gromov product under the graph distance. Okay, so this is, this is a definition. So any two x and y, xy_r be the Gromov product of x and y under the graph distance and t with respect to the base point r. So again, now you are probably totally confused, so I'll show you a picture in the next slide. So here's the picture. So our space S are these black dots. This is our space S. And you build a tree on top of that. Okay? So our space, so the hierarchical clustering is these two form a cluster, these two form a cluster, this is a cluster by itself, this is another cluster, these two clusters, and then these three form the higher level clusters and so on. So this is a hierarchical clustering. And the Gromov product is basically this. So if this is your point X, this is your point Y, it's the overlap of the two paths leading from these 2 points to the root. Okay? So that's the length of the overlap. So that's the Gromov product of X and Y. So you can see this, that the distance of x to the root plus the distance of y to the root minus the distance between x and y divided by 2 is the Gromov product. So this path is just the Gromov product of x and y. So here is what we define as distance from tree. So the space, our space S with a probability measure and a similarity function is delta tree-like if this is less than delta, where this infimum, so x and y are independent S-valued random variables with law P, and the infimum is taken over all alpha positive and all rooted trees that are compatible with this space. Okay. So this is so what you do is you take your space, you look at all rooted trees which are compatible with space, so all possible hierarchical clusterings, and you look at how well approximated is the similarity function by the Gromov product on this tree times some linear factor. Okay. So if this is small, if this coefficient is small, this tree of SFPS is small, it means that there is a tree so that the similarity function is is approximately with high probability. So if you take 2 points x and y from this probability measure, the similarity function is approximately equal to some constant times the Gromov product of these 2 points on this tree. So there is, you can express this similarity function as some function on the tree. And note that it's for x and y with law p. So it may not be true for all x, y. So with high probability, this is true. So how well can the space be embedded in a tree? Remember in the original definition of Gromov hyperbolicity, the embedding was an isometric or almost isometric embedding with some error. Here, everything is the average sense, so you have to give a different definition. So what is an isometry in an average sense? So this is what is one possible notion that, so you say that two spaces are isometric if some inequalities hold for all x, y, and here I'm just saying that the inequalities hold for most x, y. So with high probability, the inequalities will hold. Okay. So if S is a metric space and little s is a Gromov product with respect to some base point, then this S is delta tree-like for some small delta, if and only if it is approximately isometric to a real tree in an average sense. So this is, even if you didn't follow the definition fully, you can take this as the summary that it's delta tree-like, the space is delta tree-like if and only if it's approximately isometric to a real tree in an average sense. So here is the main result. So given any epsilon, there is some delta depending only on epsilon, so that if the hyperbolicity is less than delta, then the tree-like nature is less than epsilon, this coefficient. And conversely, given any epsilon, there is some delta, so that if the tree coefficient is less than delta, then hyperbolicity is less than epsilon. Okay. And this does not involve the space or the similarity function or anything. It's completely independent of everything, dependence of delta on epsilon. And this approximate embedding into a tree is given by this theorem, doesn't have this factor of log of the cardinality, so it holds for any infinite space as well. So it's completely free of the space. To get the result about spin glasses from this result, you just take S to be the appropriate function of the overlap. So it can be just the overlap between two configurations, or it can be the absolute value of the overlap for the Schenker-Kirkpatrick model. So you just plug in whatever function satisfies the Parisi ansatz, you plug that in. And since the final remark is that since any Gromov hyperbolic space is also hyperbolic in the average sense, so the implication follows in one direction. So if you actually have a Gromov hyperbolic space, you also have an average Gromov hyperbolicity. This theorem implies a new embedding result for Gromov hyperbolic spaces. So the original theorem that I showed you had this log S factored there, but this one says that if you take a Gromov hyperbolic space, let's say a finite space, and you put a probability measure, let's say the uniform measure on that space, on that finite space, and then you have this embedding theorem which does not involve this log factor. Okay? So you can take n to infinity, and you have this average notion of hyperbolicity. Okay? So this is the main result that you have, that given any epsilon, there is a delta, and the dependence of delta, this is pretty bad. This is this tower type thing that you have from Szemeredi's lemma. So this is, don't ask me about the dependence of delta on epsilon. Okay. So here is the proof idea. So take any t, let gt be the graph on S that puts an edge between x and y if and only if the similarity is bigger than t. So you have a similarity function on this abstract space, and you put edges between two nodes if and only if. So let's consider a finite space for now. The similarity is bigger than some threshold t. So if the space is zero hyperbolic, then this GT is exactly a disjoint union of cliques, because if Sxy is bigger than t and Syz is bigger than t, then the zero hyperbolicity will imply that Sxz is also bigger than t. So the graph will be, if there is an edge from x to y and an edge from y to z, then there's an edge from x to z. So that will imply that the graph is a disjoint union of cliques. Okay? So you may expect that if the space is delta hyperbolic in the average sense for some small delta, then also this GT is approximately a disjoint union of cliques, in the sense that you can delete a small fraction of edges or add a small fraction of edges or both and get an actual disjoint union of cliques. Okay? So you can expect this. However, such statements are notoriously hard to prove. So for example, this is a famous result known as the triangle removal lemma. So it says that if you have a graph on n vertices that has order n cubed triangles, then it can be made triangle-free by removing little of n squared edges. So there's a small fraction of edges that you can remove and make it completely triangle-free. Okay. So if it's almost triangle-free, you can make it completely triangle-free by removing a small fraction of edges. That sounds like a very intuitive statement, okay? But it's very hard to prove. And by now, combinatorialists will say that this is standard, but it's still a hard proof. So this is exactly along that line. So what we do is that we prove this statement that this graph GT can be slightly modified to make it a disjoint union of cliques using Szemeredi's regularity lemma. But it involves much more work than we initially anticipated. So this, so you have to really build these cliques step by step, and you have to first apply the regularity lemma, and then so just to tell you what the regularity lemma is. So the regularity lemma is that given any graph, you can any undirected graph, you can break up the vertices into a small number of blocks. So given any epsilon, you can divide up the vertices into blocks where the number of blocks depends only on epsilon. So it'll grow as epsilon goes down to 0. So you have this finite number of blocks depending on epsilon, so that most pairs of blocks, between most pairs of blocks, the edges are distributed approximately like a random graph, okay? So between any block I and any block j, there is a number Pij, so that the edges between the block I and block j are approximately like IID, they are like IID Bernoulli variables, so each edge is present or absent with probability Pij or 1 minus Pij. And they're like independent. So this has a precise sense in which this is true. That is, if they were independent, you would expect that the same fraction would hold if you take sub-blocks. So if you take two large blocks, and you take a smaller, a sub-block and a sub-block there, then the fraction of edges between the sub-blocks should also be approximately Pij. So this is how it is expressed, this random distribution of edges. And now, for example, this first thing, the order of n cubed triangles, little of n cubed triangles, if there are almost no triangles, then it can be made triangle-free by removing little of n squared edges. This can be proved using this randomness. So suppose you actually had a random graph where the edges between blocks were random, then you'd be able to prove such a statement. And then you transfer that intuition to a non-random graph to get this result, okay? So this is similar. So you have this. And so now what you do is for every t, you have this graph GT, and which is approximately modified to make it this joint union of cliques. And then the second challenge is to construct these cliques in a way so that there is this desired hierarchical clustering. So the cliques should be, so for a certain t, you have cliques, and for a higher t, you have smaller cliques, but those smaller cliques should be components of the larger cliques. So you have to construct it in that manner. And you have this full construction then. And of course, you don't do it for all t, you do it only for a finite set of t, depending on your epsilon. So this is roughly how the proof goes. That you take for every level t, you construct a graph on the space, and then you slightly modify it using Szemeredi's lemma and further arguments to show that it can be modified into this joint union of cliques, and this gives you the hierarchical clustering, and this is how you cluster the whole thing. Okay, so this is a proof idea. Sorry, I'm not stopping for questions because I will not be able to hear any questions. It's such a large room. So usually I stop for questions. Okay, so here is a summary. So we introduced an average version of Gromov's measure of hypervelocity on metric spaces. A space that is hyperbolic in this average sense is shown to be approximately isometric to a subset of a tree, and also in an average sense. So this approximate isometry is also in an average sense, not in the sense of quasi-isometry that you usually encounter. And this proof is based on Szemeredi's regularity lemma. And this result is used to construct hierarchically organized pure states in any spin glass model that satisfies this as in the Parisi ultrametricity ansatz. Okay. And so this has been used in many applications. in real world applications such as social networks and phylogenetic trees, and it's possible that this average hyperbolicity may be a better notion. And already, there have been attempts to study this with average hyperbolicity. So when you go beyond pure mathematical objects, you go to messier things, or you go to things that arise in probability theory, for instance, then the original notion of hyperbolicity is probably not a good idea to use because it's the worst case condition. So this is perhaps a much better thing to use, the average hyperbolicity. And so we are looking into that. Okay.
Thank you very much. So we have time for questions, so please go ahead.
So, this is wonderful. Let's imagine you have one more parameter.
Yeah.
Temperature.
Yeah.
Right, in the spin glass. So then your Gibbs measure depends on one more parameter.
Yes.
If you try to follow this clustering, this temperature, and you know that there are different cases.
Yes.
One case you have temperature chaos.
Yes.
You remove the temperature.
Yeah.
Takes completely.
I see.
And when the other case, the clustering essentially doesn't move this temperature.
Yes.
Right? So, for instance, for spherical cases,
Mm-hmm.
you mentioned the pure case where
Yeah.
you don't have chaos, it's superimposed. And as soon as you have a mixed case,
Uh-huh.
there is chaos.
Uh-huh.
So would you be able to follow that with the average hyperbolicity thing?
Like how the clustering changes as you change temperature?
At one parameter or metrics, so metric depends on the number.
Yeah, no, that's hard to say. Whenever you have chaos, you would probably expect to see some chaotic behavior in the clustering also. So the clustering will change.
So what I'm saying, so typically,
Yeah,
and in spin glasses you have it.
Yeah.
Very easy to
Yeah.
understand distinction.
yeah. Yeah, no, that's a very interesting point. Yeah, so I haven't thought about that, the chaotic behavior of the clustering. It's a very interesting thing, so I'll probably look into that. Yeah, thanks, Gerard.
Okay. Any other comment? Okay, so let's thank again our speaker for the lecture. Okay, thank you.